switching between human beings and a computer. So that's why we had to go through some of these. So we know the computer binary rules as well as the human decimal rules. So same thing. So we converted from computer language, which is in binary, signal-wise, binary forms, to decimal and then to ASCII. And then to the computer, it's from the ASCII all the way down to the binary. Okay. So the message we have here is uppercase H, lowercase I, which is high, and it has a decimal value of 32 and 105 um, respectively. And in terms of binary, you have 0, 1, 0, 0, 1, 0, 0, 0 for the 72, or the uppercase H. And then you do have 0, 1, 1, 0, 1, 0, 0, 1 for the lowercase I with a decimal of 105. Okay, great. So now let's go to the various signal encoding techniques that we have and see if we can uh, generate signals, the encoding or schemes for this message at the computer signaling level. Okay, so first of all, the computer gets the binary and then generates the signal out of that. Okay, so based on rules, and the rules are within the various signal encoding techniques. So the first technique that we had, the first scheme that we had was the non-return to zero technique, which has two forms or two techniques underneath it. One is the non-return to zero level, so in this case for H, uppercase H, and then we're going to have the same thing for lowercase I, and then we do have the non-return to zero inverted for H and then for I as well. So we have two techniques under the non-return to zero. So we have two schemes under, or two available options or signal encoding forms under the non-return to zero techniques. And the first one is the non-return to zero level, and then the non-return to zero inverter. I want to generate the signal for these two forms that we have on the non-return to zero for the message that we have. Okay, so if you were to send a message high, the question is how does the computer interpret it in a signal level or in a digital signal level using the various encoding techniques that we have. Okay, so for the non-return to zero, the rule states that go through. If you don't know what the rules are, go through the slides. I will tell you. For the non-return to zero level, the rule states that all zeros must have a high voltage pulse start. Now I've used a +5 and a 0 to illustrate the voltage pulses. If you notice, I was saying that computers generally use either voltage pulse or currents to handle their their signaling. Okay, now I'm using +5 over here because most of our devices, especially our mobile devices, uses 5 volts for charging, as well as running to power some of the various integrated circuits on the board. Okay, so that's why I'm using the plus or the 5 volts here. Okay, so keep that in mind. And since signaling is all about graphs, we have to have our graphs in place. You have to have our graphs in place. I'm just trying to put I forgot to put the voltages on some of these stuff. Okay. So we are keeping on, we are just on the null return to zero technique and going through its two schemes or options that are available under the null return to zero technique. And the first one is level. So according to the null return to zero level, the rule states that when a bit sequence is in an off state, um, the signaling must have a higher voltage pulse. So in this case, a high voltage pulse will start at +5. So we have 5 and then 0. Okay, so 0 volts and then 5. 5 will be the highest. So the rule states that an off-state bit should have a high voltage signal level. Okay, so now to do that, I'm just going to be using draw borders, and let me pick the thickness of the line of the borders, so at least we can see them. I'm going to pick the thicker one. So since it has to be high start or high voltage for 0 volt off state, I'm going to just drop right over there. So that's a high voltage start. Okay. For a bit in an on state, it should have a low voltage pulse, which is in this case 0. So I'm just going to put let me move the cursor this line. Oh, so yeah, I have my X and Y, so that's obviously my Y axis and then an X axis. Okay. So with that said, you can now you can join the signal here. So now we have high for zeros or for off state, and then low for on state. So the same applies: high, high, low, high, 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 and then you can just join them. So that would be the null return to zero level of signal for the uppercase character with H of the message that was sent or that we have. Okay. So what about for I? The same rule. 0 or off state, high voltage pulse, on state, low voltage pulse. One again, or on, low voltage pulse, off, high voltage, low for one, and obviously that, and then low. So we have high, low, low, high, low, high, high, low. And you can just join them up or link them together to give you the various signal that you need, or the signal that you need for the message. So this is what a computer would actually transmit over a medium or within the circuitry boards as signal for for a technique that relates to non-return to zero level. Okay, so I hope everybody got how I arrive at some of these things. I'm just applying the rules of the non-return to zero level, which states that when a bit is an off state, you have a high voltage pulse. When it's an on state, you have a low voltage pulse. So obviously zeros are going to be high, ones are going to be what? Low. So you have high, low, high, high, low, high, 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 because there's zeros here. And then for I, lowercase I, it's high, low, low, high because of 0, low, so 1, high, high, zeros, and low for 1. So you have high, low, high, low, high, low. That sounds like a rhythm, huh? Okay, so that handles it for the no return to zero level. Now, what about for no return to zero inverted, which is the second uh, option, the second scheme option within the no return to zero inverted? Okay, so now the rule for the no return to zero inverted, it's not the exact opposite. Keep that in mind of the no return to zero level. But the rule states that when you do have a zero voltage pulse or a bit in an off state, you start with what? A low voltage start. Right? And then you have transitions. Transition only happens when you're going from um, uh, 0 to 1 or 1 to 1. 1 to zeros, you stay at wherever the signal level is at. So keep this in mind. 0 has a level voltage pulse or a 0 voltage pulse for off state. And you transition when you're going from 0 to 1 or 1 to 1. But 1 to 0, you do not transition. You basically stick at wherever the voltage pulse at. Okay, so let's go through that. So we are moving from 0 to 1, and based on the rule, we have to transition. So transition means you're moving from the current state to a different state, and the only different state we can have here is what? A high voltage pulse state. Okay, now we have a 1 to 0, and the rule says from 1 to 0 there's no transition. So in that sense, we do not transition. You just stay at wherever you are. So if the current state was at high, it means that at this level it will still be high because we are not transitioning. Now we have a 0 to 0. The same rule. We do not transition from 0 to 0. The transitions only take place, which is transitioning from one state to another, only takes place when you're moving from 0 to 1 or 1 to 1. So it means that 1 to 0 and 0 to 0 they are not transitioning. There's no transition. You just basically stay at wherever you are. So since we have 0 to 0, we just stay exactly where we are. But here we do have 0 to 1, and it has to be a transition. Now we have at the high voltage pulse, or we are at plus 5 volts. And since we are going from 0 to 1, we need to transition to what? To a low voltage pulse. So low voltage pulse. 1 to 0, no transition. So we still stay at the same spot. We still remain at our current state. 0 to 0, same thing, no transition. 0 to 0, no transition. So for the no return to 0 inverted for uppercase H, this is the signal that is going to be generated by the computer using the no return to 0 encoding technique, or no return to 0 inverted technique. It would be low, high, and then low. Okay, now let's go through it for lowercase I. So the same thing, so 0, it starts off with a low voltage pulse. Now from 0 to 1, you transition. 1 to 1, there's 1 to 1, and keep the transitions only happen from 0 to 1 and 1 to 1. So in this case, we have to transition from our current high voltage pulse state to a low voltage pulse. Okay, now 1 to 0, no transition, so we just remain there. Now we have 0 to 1, we have to transition based on the rule. So we are from low to a high now. 1 to 0, no transition. So we're just there. 0 to 0, no transition. But we have 0 to 1, there has to be a transition based on the rule. So from high to a low. So this is what you're going to have for your null return to zero inverted for lowercase I. That would be the signal that will be generated for the computer to send down the circuitry board either through when it's going out, either through the airwaves or through a copper wire medium, a twisted pair copper wire medium. And when it comes to fiber optic, it's a different signaling issue, a completely different signaling process. Okay, but for mostly conducting electricity conducting mediums, this is probably a shape that will take. Even within the airwave, it will not take the shape. It would have an analog shape, by the way, depending on how uh, uh, the the analog signal the reference is for that particular encoding technique is designed. So it will take that shape or that form. Okay, so that's how we get to or you get your signal generated for non-return to zero level for the message high and for the two forms, which is the level and then the non and then the inverted forms for the non-return to zeros. Okay, now let's move on to the next technique, which is the multi-level binary. So multi-level binary, it's always about the word multi-level means we're going to be switching between two states, two different voltage levels. So that's why you have a plus and a minus. Okay. With this, we only have more or less one state, one voltage state. It's always it's more or less at the positive level. While with the multi-level, we're going to be switching between two states, a positive voltage form or state, or to a negative voltage pulse level or state. Okay, so whenever you see the multi-level binary, it just means that you're going to be switching between multiple states. In this case, from a positive to a negative. Okay. I wanted to consider the zero as part of maybe in a way you can consider as part of the voltage levels. So in that case, for the no return to zero levels, or for no return to zero part or techniques, you have two voltage levels. But the fact of the matter is, we don't consider it multi. You can't use multi-level over here. That's the reason why I don't think most people prefer to use that word of having two voltage states for the no return to zeros. It's usually at the multi-level one that you say that's where you say using different voltage states because the reference here is you do have you do have to switch between completely different states. You one we are within a positive state and the other you're within a negative state. Okay, so that's why hence the multi-level. We're switching between two completely different levels of voltage peaks or voltage levels, a positive and a negative. Okay, so I do have my plus 5 voltage and minus 5 voltage. Now let's go through this. So the first, all the various other techniques that we have do have two schemes underneath them. Okay, keep that in mind from the textbook or the slides. They all have two schemes underneath the various techniques. And so the same applies to the multi-level. And the first one under the multi-level is the bipolar AMI, which is the bipolar alternate Mach inversion. So the AMI represents alternate Mach inversion. Okay, so the bipolar AMI. Now let's go through the signal uh, for the character uppercase H, what it will look like. So we have to go to the rules as well. We have to apply the rules to it. Now the rule states that For the bipolar AMI, 0 or off-state bits have low voltage pulses, and on-state bits have uh, not necessarily uh, uh, high voltage pulses, but the transition is the key here. So anyway, let's go to the transition part. That would help us explain or put together whether whether on state needs to be at a high voltage pulse or not. Okay? But the rule states that all off states must have a low voltage pulses. In this case, 0 or level voltage pulses. Okay, for all zeros. So even with that rule, we can easily start with applying that rules to all the off states. So this is going to be level, uh, level, 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 and level. Because the rule states that all these zeros must have a level voltage pulses. Now, it's the ones that have got the tricks, that have got the alternation. So the alternation only happens on ones. So which means if the first on state, which is 1, is at a high voltage pulse, the next on state at wherever the bit sequence, at wherever it occurs at within the 8-bit sequence or between the sequence of that particular bit message, it should alternate from the high state to a negative state. Okay, so in this case, the first on state has to be a high, and then the next on state has to be what? A negative, and then the next one, if we have another one, then will be a high or a positive state or a high voltage pulse state. Okay, so yeah, once you have that, then you can just join them up or link them up, and then you do have your uh, bipolar AMI for uppercase H. Okay, so the alternation only happens on the on states. So if the first one is high, the next one has to be a negative, or has to switch its state completely. Okay, so in this case, a negative. Okay, and then the zeros are always level. So for lowercase I, the same concept or the same rules apply. So let's deal with the off states first. Level, 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 level. It's the one that gets alternated. Okay, so here we have a high, a negative, a high, and a negative, and you just link them up. Oh, I did this wrong. So it's only this side here, that, and that. Okay, so that will be the bipolar encoding scheme, AMI bipolar. So bipolar AMI under the multi-level binary technique for uh, lowercase I, and then for uppercase H, it would look like this. Okay. If you're still wondering, again, I'm just following the rules of the various uh, encoding techniques that we have. They all have rules that you need to comply by. That must be applied to the various bit sequence that you have. Okay. So keep that in mind. For the bipolar, under the multi-level binary, you're only alternating on the ones, and zeros are always going to be in a level voltage pulse state. whereas the ones who alternate between positive and negative voltage pulses, positive high voltage pulses and negative high negative voltage pulses. Do you know what I mean? So a -5 would be a high negative, and then a +5 would be a high positive. Okay. Okay. Now the second scheme under the multi-level is the pseudoternary. So now let's go through that. And the rule for the pseudoternary is more or less the exact opposite of the bipolar. So in this case, all state bits are actually going to be the ones you alternate, and then the off state bits or the off state bits are the ones that you need to alternate, and the on state bits are the ones that needs to stay at level voltage pulse or 0 volts. Okay, so with that rule, we just go through and know that the ones are going to be purely level right here, and then it's the zeros that we're going to be alternating on. So the first off state has to be in a high state, and then the rest will have to alternate. So from low to a high, and then to a low, to a high, and then back to a low, and we just connected the signal. There you go. So that's what you have for the pseudoternary. That was like a very interesting signal, huh? Like a staircase, you climb up, you climb down, you go all the way up, climb down, all the way up, climb down. Kind of signal. It's quite exciting steps or interesting steps. Okay, what about for um, a lowercase I? So once again, it's all the ones that needs to be level, and then the off states would have to be, or the zeros needs to be the one alternating. So from a high to a negative, back to a positive, down to a negative, and then you just connect that, or connect the graphs. Okay, so now we do have uh, the the signal encoding techniques for the two groupings that we have. So there are four groupings, right? So the first two have been done with all uh, their various schemes that they have. Okay, so we're done with those ones. The next one, it's uh, the biphase technique, right? Which has the Manchester and then a differential Manchester. Okay, so for that one, we obviously do, since with that one you switch, you alternate within mid bits. So I'm going to have to use a completely different graph for that, since these are single cells I'm using for each bit, and I need a middle bit, and I can achieve that with just single cells. I need to basically, to get the mid bits going on or transitioning for the biphase techniques, I need to generate a different sheet that can accommodate two cells for one bit, for a single bit. Okay, so let me see if I can put that together. And it's the same rule. We're going to use the same information, the same message, but obviously having different technique forms. So I'm going to copy this here, and then create a new sheet. and paste it over here.